Hi everybody, welcome back. In our last video we discussed how Gauss's law can be used to motivate Gauss's theorem, aka the divergence theorem, in multivariable calculus. And what I'm hoping is that that discussion can be something that you can use to think about and better appreciate the fact that charge sources result in net electric fluxes through closed surfaces. And a reminder also that that enclosed charge technically is a volume integral, but when we actually perform our calculations, we're going to find ways of simplifying that into one-dimensional integrals. So here's the form that we're actually going to use. And the left side of this, from this point forward, the left side of this equation is going to be trivial. It's something that you'll be able to do in your head very quickly. It's the right side of the equation where the trouble is going to arise, as you'll see later in this video. So the surface integral itself is actually very easy. The right side is hard. So we have to use symmetries in order for Gauss's law to work. Otherwise, we're going to have situations where in some parts of our surface, the angle between the electric field and the normal to the surface will be different compared with other parts of the surface. When that happens, Gauss's law won't be able to be used, and we'll have to give up and call it a day, or send it to a computer simulation to allow us to approximate the answer. But it turns out even if you can calculate the surface integral using those more complex methods, if the symmetry goes away, you'll just need to recalculate the surface integral at each position for which you need the electric field. In other words, just because you have some funny symmetry that's not one of our basic symmetries at the surface, doesn't mean that that symmetry is still going to be valid at certain distances farther away from the surface. So that's something else to consider, which is why computer simulations would be necessary in those complicated situations. As a reminder, the three basic symmetries are planar symmetry, things like slabs or sheets of electric charge in which the charge density is uniform throughout the sheet, or slabs where you have a bunch of sheets stacked on top of each other, or cylindrical symmetry where the charge distribution is independent of your height position along the cylinder and independent of your angular position along the cylinder, though it might be dependent on your distance from the axis of the cylinder. And then there's spherical symmetry, where the charge distribution is independent of any of the two angles, the axial angle and the drop angle, but could be dependent on your distance from a central point. So we're actually going to analyze spherical symmetry first. But if you're watching this on video, which if you're watching this then you are, this would be a good time to pause and maybe get with a partner who's also watching the video and discuss how charge density may and may not vary with respect to certain coordinates for each of these symmetries. It's something that I just stated, but it's something that you need to remind yourself. So I'll give you a minute to pause. And now, again, just a final reminder, with planar symmetry, the charge distribution, let's say that the plane is in the xy plane, the charge distribution is independent of x and y. However, for a slab, it might be dependent on z. For cylindrical symmetry, let's say the axis of the cylinder is the traditional z-axis, then the charge distribution will be independent of your z-coordinate, but it might be dependent on some sort of radial coordinate. And in spherical symmetry, if you're dealing with your r, theta, phi type of spherical coordinates, then the charge dependency would be independent on theta and phi, but could potentially be dependent on the radial coordinate r. Okay, so there we go. There's our summary of this. And now it's time for us to start looking at how we will actually solve Gauss's law. So first, we're going to be applying it to spherically symmetric situations. And in using Gauss's law to solve these problems, we are going to be setting up what we call a Gaussian surface around our charge distribution. In spherical symmetry, the Gaussian surface will always just be an imaginary sphere. For cylindrical symmetry, it will be an imaginary cylinder of finite length. And for planar symmetry, it will actually be anything at all as long as the top and bottom of our surface is parallel to the plane and the sides of our surface are perpendicular to our plane. So, in any case, our Gaussian surface will be a closed surface that surrounds the charge distribution. And in order for the Gaussian surface to be useful, two things must be true. The symmetry needs to match the symmetry of the charge distribution in some way, which we've already described how that's going to work. And the electric field must be either normal to or tangent to all parts of the surface. When we get to slabs and planes, our Gaussian surface will be such that two of the surfaces, the electric field will be normal to our electric field, and the surface that connects the two surfaces will be tangent to the electric field. So, if you're not able to do this, you won't be able to use Gauss's law. Here's an example of a bad problem. Gauss's law would not be able to be used to solve for the electric field at some arbitrary position in the case of this surface. Here, I have drawn the actual charge distribution in thicker writing, but I try setting up my Gaussian surface inside, and it's like, well, okay, fine, that's what it looks like there, but outside it will end up having a somewhat different shape. In other words, you're not going to be dealing with the necessary symmetry. So, if you had some charge distribution that looked like this, you would have to use computational techniques in order to be able to solve for the electric field at an arbitrary position in space. So, tips for applying Gauss's law in general. No matter what type of charge distribution, assuming that it's one of the valid ones. Determine the symmetry. In other words, is it planar, is it spherical, is it cylindrical? Choose and draw a Gaussian surface with the same symmetry. And don't worry about enclosing all the charge. I mean, if you're dealing with an infinite plane, you're not going to be able to draw an infinitely large surface. It would take too long. But make sure that every part of your Gaussian surface is either parallel to or perpendicular to the electric field. And then you'll use Gauss's law. So, let's see how that goes. Our first example, which is trivial. Use Gauss's law to determine the electric field magnitude at any distance r from the center of a point charge q. Wait a second, we already know this. Well, the point is we're going to see how Gauss's law is used for something like this so that we can then extract the general procedures for more difficult problems. So, point charge involves spherical symmetry, as long as the charge isn't rotating. And thus, we can imagine our Gaussian surface in the shape of a sphere of radius r. Remember, Gaussian surfaces are pretend things, but you can still use them to figure out what would be the flux through this pretend surface, and then use Gauss's law to relate that flux to the enclosed charge divided by epsilon naught. Well, the point is, we already know the enclosed charge. We want to figure out the electric field. In fact, since we know the enclosed charge, we know the electric flux. It's q over epsilon naught. But that's equal to the surface integral of E vector dot dA vector. And from that, we're going to get what E vector is. Now, keep in mind, since it's a point charge, this is completely independent of angle. The electric field is independent of angle, whether it's an azimuthal angle or a drop angle, like theta versus phi, in other words, or phi versus theta, depending on what you want to call going from 0 to 2 pi and what you want to call going from 0 to pi. Usually I call phi the angle going from 0 to 2 pi, because most physicists do that, though I know multivariable calculus textbooks, or at least high school calculus textbooks, often do it the other way around. In any case, we don't care because our electric field is independent of those angles. It's only potentially dependent on r. So, remember, in this case, well, in all cases, the left side of Gauss's law is easy. It's just E times A. The right side, in this case, is also easy because we know what the enclosed charge is. It's called lowercase q. So we just wrote it down in place of q enclosed. So, dividing both sides by 4 pi r squared, we get that the electric field is equal to q over 4 pi epsilon naught r squared. Wait a second, 1 over 4 pi epsilon naught is called k. So E equals kq over r squared, just like we've obtained in numerous examples before. The point, though, is how we got this final answer. This is the same technique that we're going to use to solve more complicated problems. So again, the left side of Gauss's law is very easy. In this case, it's just E times A. In fact, when you're using Gauss's law to solve for the electric field, the left side is always E times A, where A is the surface area of your Gaussian surface, at least the part of it that is perpendicular to the electric field, such that the unit normal vectors are parallel to the electric field. So remember, the point was not to find the flux. We already knew the flux. The point was to use that to find the electric field. Now, how about the electric field at all distances r, little r, from the center of a conducting sphere of radius big R containing charge big Q? Well, here, again, it's actually relatively easy. Because remember what a conductor is. A conductor is a situation where, as a result of being a conductor and charge being free to move anywhere it wants, it moves to be as far away from other charges as it can be. Well, it can't go any farther away than the surface, so all the charge aggregates on the surface. And being on the surface, that means that any Gaussian sphere of radius little r less than big R is not going to contain any charge. Which means that since the integral of E vector dot dA vector is equal to enclosed charge over epsilon naught, and the enclosed charge is 0, that means that since the area is presumably not 0, the electric field must be 0 in order for the flux to be 0 if little r is less than big R for a conducting sphere. So, since all the charge is on the surface, we get that the electric field inside of the surface is 0. Well, that's something we've talked about before. Now, since the enclosed charge for any Gaussian sphere of radius little r greater than or equal to big R is equal to capital Q, we get, well, again, starting with Gauss's law, we have that the electric field on the outside part is equal to, well, since electric field on the outside part times the area of your Gaussian sphere is equal to big Q over epsilon naught, dividing both sides by 4 pi little r squared, we again get that the electric field outside of our Gaussian, of our actual sphere is K times big Q over little r squared. Again, it's what we expected, nothing new here, though we now realize that the reason we should have expected that is because of the fact that inside of the sphere there's no enclosed charge. That's why the electric field inside of a conductor is 0, because any Gaussian surface that you can set up inside of that conductor is going to contain no charge. How about a uniformly charged sphere? It turns out this is actually relatively easy, but not as easy as the previous ones, because here we actually have to calculate something. Calculate the electric field at any position little r from the center of the sphere. Well, outside of the sphere, we just did this. Outside of the sphere, your imaginary Gaussian sphere, which contains charge big Q, is just going to be, the electric field is just going to be K times big Q over little r squared. So there's our electric field outside of the sphere. Now, what about inside of the sphere? Inside of the sphere is where we really kind of need to show our drawing of our Gaussian surface. So let's say that my sphere of charge, my uniform sphere of charge, is gray colored. I'm going to make my imaginary Gaussian surface purple colored. Now, if little r was greater than big R, then my purple sphere would be bigger than my gray sphere, and it would just contain a total charge of capital Q. But with little r being less than big R, since this is a uniform sphere, this gray sphere has charge distributed uniformly within and out to the surface, that means that depending on my radius little r for my Gaussian surface, different values of little r are going to contain different amounts of charge, as long as little r is less than or equal to big R. So that's where our calculation is going to come in. So here's what we're going to do. What we're going to do is we're going to imagine little bitty shells of radius little r prime. as long as little r prime is less than little r. So the idea is that each of these shells will contain a different amount of charge. Why shells? Why not just do the whole sphere itself? Because charge distributions aren't always uniform. What we're trying to do is we're trying to treat increasingly difficult situations using the same technique to show how this technique would be used in general. So, yes, it's true that you could actually just use geometry in this situation to figure out the enclosed charge as a function of little r and use the ratio method without having to use calculus. We are going to use calculus here, though, so that you can see how the calculus would be used if the charge density was not uniform on the inside of this sphere. So each shell, so you can imagine that we have, say, some arbitrary shell of radius little r equals r prime, where r prime is less than or equal to little r, and say going out from the center of this out to some arbitrary position here. So the radius of your shell would be r prime, little r prime that is. Well, what's its surface area? We care about the surface area because we want to know the volume of the shell. Well, the surface area of such a shell is just 4 pi little r prime squared. The thickness of the shell is d little r prime. Well, that means that the actual volume of our shell is 4 pi little r prime squared times d little r prime. Why do we care about that? Because we want to know how much charge is contained in that particular shell. And then we're going to add up all of the shells by slapping an integral sign in front of it. So the amount of charge in each shell is given by the charge density at that particular radius. Now you can see why we're using shells, because if the charge density was not constant, then it would be a function of r prime. Here it is constant, so it's just rho. But the charge density is rho, so at that particular radius, it's rho of r prime. So the amount of charge that's contained in that particular shell that has a thickness of d little r prime, and has a radius of little r prime, is just rho of r prime, little r prime, times that infinitesimal volume, which is 4 pi little r prime squared d little r prime. So if you know what rho is, you just multiply it by this volume element, as we call it. Well, here we know what rho is. Rho is constant. In fact, rho isn't just constant. We can figure out what it is. Since the charge is uniformly distributed, rho is just equal to the total charge, Q, divided by the volume of the sphere, 4 4/3 pi big R prime cubed. Okay, so let's see how this is going to go. We'll write out our Gauss's law. Well, the left-hand side is easy. It's E times A, where A is 4 pi little r squared. That's the Gaussian surface. Inside of our Gaussian surface is a bunch of little shells, each of different radii little r prime. And again, keep in mind that the enclosed charge is not capital Q. That's what we're trying to figure out. We're using spherical symmetry here, though. In other words, the polar angle phi and azimuthal angle, this should say azimuthal angle theta. The charge density is independent of theta and phi. So we do need to fix this so that it actually says theta instead of phi. So I'm going to now say fix it. And lo and behold, PowerPoint has done its magic, and it correctly states it. Again, by azimuthal angle, and I might have misstated this earlier in the video, but by azimuthal angle, I mean the drop angle from the traditional pole. In other words, it's the angle that's between 0 and pi, going from so-called North Pole down to the South Pole. And the polar angle is the traditional polar angle going from 0 to 2 pi, back from polar coordinates. So again, each shell has a volume of 4 pi little r prime squared d little r prime, and that's what we're going to be using here. So the enclosed charge is equal to the sum of all the little bitty enclosed charges. What's a little bitty enclosed charge? It's the amount of charge that's contained in each shell of radius little r prime. Well, we want to add up all of those little shells from the center all the way out to the radius of our imaginary Gaussian sphere that has a radius of little r. So, well, again, we know what rho is because it's a constant charge distribution. It's just Q over 4/3 pi big R cubed. And again, that volume element is 4 pi little r prime squared d little r prime. It's going from this first integral to this second integral, where we have turned this from a multivariable calculus integral into a single variable calculus integral by using the symmetry of the problem, the fact that the charge distribution is independent of phi and theta. So now we can pull out constant terms. The 3q over big R cubed comes out. The 4's cancel, the pi's cancel. So all that's left is, inside of the integral, is little r prime squared, d little r prime. Well, that's an easy thing to integrate. That's little r prime cubed over 3, canceling this factor of 3 that we have out here. Where do I want to go to? Well, we want to know how much charge is inside of our Gaussian sphere of radius little r, which means we are adding up all the shells going from little r prime equals 0 all the way out to little r prime. All the way out to little r prime equals little r. And when you do that, you get big Q times little r cubed over big R cubed. Now, people who are used to using the ratio method would have arrived at this result instantly using geometry. And by instantly, I mean less than one line, probably. Well, okay, one line. You can't have 0 lines. You have to show your work. But in any case, we got this using calculus here. The point is, we would still be able to get this using calculus if the charge distribution was not uniform. The ratio method would only work if it was uniform. So, there we go. Now we know what the enclosed charge is. So, again, we've worked out the left side of Gauss's law. That's trivial. We worked out now the right side of Gauss's law, at least for the enclosed charge. So we plug that in. So there's the left side on the left. There's the right side on the right. And divide both sides by 4 pi little r squared. And you get that the electric field inside of this uniformly charged sphere is k big Q little r over big R cubed. In other words, it's directly proportional to your distance from the center. Hopefully that makes sense, because you know that electric fields for point charges and spherically symmetric charge distributions fall off as 1 over r squared, but inside of your uniform sphere, the farther you go from the center of the sphere, the amount of charge inside of a Gaussian sphere goes as little r cubed. So little r cubed versus 1 over little r squared, those are going to mostly cancel, leaving you just with a factor of little r. So not incredibly surprising after you start thinking about it. So here is our overall final answer. The electric field, as a function of position from the center of our sphere, is k big Q little r over big R cubed times r hat for little r less than or equal to big R, whereas if it's greater than or equal to big R, it's just k big Q over little r squared. So notice that at the surface, little r equals big R, because of the fact that we had a continuous charge distribution with a well-defined charge density, you ended up getting a match at the surface. In other words, if you go back to this equation, plugging in little r equals big R gives you a cancellation, and at the surface you get E equals k big Q over big R squared. That's what's going to happen anytime you have a continuous charge distribution. A spherical shell, or a spherical conductor, is not going to be a continuous charge distribution. There you only have the charge at the surface. You can still turn that into a volume charge density, though, using a little bit of deeper mathematics, something called Dirac delta functions. But we're not going to have anything much to say about that in this course. That's something you're going to get into in more detail if you are a physics or engineering major and you end up taking 300 level electromagnetism when you are in college. Now, so the electric field was continuous with a charge distribution that didn't spike because of the fact that we had that continuous charge distribution. In the case of a spherical shell that is, there would be a spike in the charge distribution right at the edge of the sphere, and that would be it. Now, nonetheless, when we get into chapter 28, there's a quantity called electric potential, which is actually continuous no matter what. Even if you have a discontinuous charge distribution, the electric potential will always be continuous. And you'll see why when we get into the next unit. But for now, I'd like us to turn our attention to a non-trivial example. Let's say you have a sphere of radius big R and total charge big Q, but the charge is distributed in a non-uniform manner, such that the charge density is proportional to 1 minus little r squared over big R squared, where little r is your radial coordinate, going out to the edge of the sphere with radius big R. So here's the idea. We know what the charge density is proportional to, but we don't know what it is equal to. So first, we need to come up with an equation for the charge density itself. Let's see what that looks like. So we're going to say that the charge density is proportional to 1 minus little r squared over big R squared. Well, what that means is that it's equal to 1 minus little r squared over big R squared times an appropriate constant, which I'm going to call rho naught. Question is, what's rho naught? Well, remember, the total charge is equal to the sum of all of the little bitty charges. So what we need to do is we need to integrate our expression for the volume charge density and set that integral equal to the total charge, capital Q. Well, we're going to integrate from r equals 0 to big R. And here, I really don't even need to call it little r prime. I could just call it little r. But in any case, this volume charge density is proportional to, well, little r, I should be consistent here and call it little r prime, but whatever. But there's our expression for rho. So we plug it in. The constant rho naught comes to the outside. The stuff that's not constant, in other words, the stuff that can be multiplied by integration variables, needs to stay inside. And this 4 pi little r prime squared d little r prime, remember, that is the volume of a shell of thickness d little r prime with a radius of little r prime. So I could bring the 4 pi outside. I'm going to do that. And what's left after distributing through the r prime squared is we have an integral going from the center all the way out to the edge. All the way out to the edge, because the idea is we know that this must be equal to the total charge. It's got to be equal to the total charge. So we're going to find the value of rho naught that makes it equal to the total charge. So we perform our integration magic, and upon doing so, we get that this integral evaluates as r prime cubed over 3 minus r prime to the 5th over 5 big R squared. But when you plug in your integration bounds, first of all, the 0 and it ends up integrating out as 0 because this is just a polynomial. But plugging in big R, we get big R cubed over 3 minus big R to the 5th over 5 big R squared, which is big R cubed over 5. Well, a third minus a fifth is 8/15. Sorry, it's 2/15, my bad. 2/15, but you end up getting an 8 pi over 15 once you distribute through the 4 pi. So a third is 5/15, a fifth is 3/15, so 5 minus 3, 2, and then times 4 pi gives you the 8 pi rho naught big R cubed over 15. So remember, what was the point in doing this? We needed to figure out what rho naught was, because this was just an arbitrary constant. But now we know what it is. You solve for it, and it's 15 big Q over 8 pi big R cubed. So now we know what rho naught is. We're just going to call it that until the end of the problem, and then we'll plug it in later. So now, first, consider the trivial situation outside of the sphere, where little r is greater than big R. Little r being the radial coordinate, big R being the radius of the sphere. Well, again, that's trivial because we already know it. It's a spherically symmetric charge distribution. That's just going to be E equals kq over r squared. That is little r, and that is big Q. And that's because, again, total charge enclosed by an imaginary Gaussian sphere of radius little r is big Q. Its area is 4 pi little r squared. So there's the left side of Gauss's law. Solve for E, and you get k big Q over little r squared, just like a million times before. What about inside the sphere? Well, that's the non-trivial situation. We're going to set up the integral again. We need to figure out the enclosed charge. Well, wait a second, I thought we already did that. That's big Q. Well, we need to figure out the charge that's enclosed in an imaginary Gaussian sphere of radius little r less than the radius of the overall sphere of charge. So in other words, instead of integrating out from the center of the sphere all the way out to the edge, we're going to integrate from the center of the sphere out to the edge of our imaginary Gaussian sphere of radius little r less than or equal to big R. The math is basically going to be the same. It's just that the integral is going to evaluate differently because we're not going to have big R's canceling anymore. But notice that, this integral is the same. It's just the bounds are different. So that's where we're at. We pull out the constant things again. There's our integral. The integrand is the same as it was when we were figuring out what rho naught is. Again, just the bounds are different. But because the bounds are different, you're not going to end up being able to cancel any of your big R's. You just have to leave it. So there's the expression for our enclosed charge if little r is less than or equal to big R. Well, again, there's Gauss's law. The left side of Gauss's law, 4 pi r squared E, where little r is how far you are from the center of the sphere, in other words, the position where you want to evaluate the electric field, equals the enclosed charge over epsilon naught, where the enclosed charge is this expression we just derived. So dividing both sides by little r squared to solve for the electric field, well, the 4 pi's cancel. That's nice. Kind of. If they didn't cancel, we would just call the 1 over 4 pi epsilon naught k, but they canceled. And also the little r squared from the denominator cancels with some of these in the numerator. So what that leaves us with at the end of the day is that the electric field at little r inside of our sphere is equal to rho naught over epsilon naught times little r over 3 minus little r cubed over 5 big R squared. So yay, we're finally done. No, we're not. Don't forget, rho naught stands for something. We still have to plug in rho naught, or at least remind people what it is. So rho naught was 15 big Q over 8 pi big R cubed. So now plugging in rho naught and working it with everything else, we end up actually having an excuse now to say that we have this 4 pi epsilon naught there, and embedded within the 8 pi epsilon naught, so that's 2 times 4 pi epsilon naught. In other words, 1 over 2 times 4 pi epsilon naught. Well, that's the same thing as k over 2. So we're left with the 15, we're left with the big Q, we're left with the big R cubed in the denominator, and we're left with the thing in parentheses. So now we're done. We finally have the electric field as a function of position, and yeah, you did not need to simplify that in terms of k or anything like that. Just leave it as epsilon naught, especially if it's on an exam where you're being timed. I just did this for the sake of neatness. So outside of the sphere, it's just kq over r squared, little r squared that is. Inside of the sphere, the electric field is 15 kq over 2 big R cubed times little r over 3 minus little r cubed over 5 big R squared. And as you can verify which is something you would need to be able to do generally on the AP exam, this will often be a 1 or 2 point problem. Verify that at the surface the fields match, which they always will if it's a continuous charge distribution. So you would plug in little r equals big R, and you'd find that the expression on the right is equal to the expression on the left. So that is how we use Gauss's law to solve spherically symmetric problems. I hope you all found this informative. Comments and questions on YouTube, and thank you all for watching. Next time we will discuss planar charge distributions. I'll see you then.